I'm going to talk about mathematical modeling as applications, how to basically construct these mathematical models. So first, this is the table of contents. I'm going to first talk about what is mathematical modeling, and then after I explain what that is, we're going to ask the question of how, and how we actually make this thing, and finally I'm going to go through our application of all of this in something called system dynamics models. So first, what is mathematical modeling? So if you look at this, plot this scatter graph here, you see the GPA versus time spent studying each per day. GPA is on the y-axis, while time spent studying per day is on the x-axis. And from this scatter plot here, we can create this best fit line, which the equation is right here. But this is a very straightforward example of what mathematical models look like. But on the other hand, these things, discrete models for in vitro tissue growth, which is actually in Mr. Pettifor's undergraduate thesis, this is also a kind of mathematical model. But the thing is that this looks quite different. This looks very different from what I previously talked about, which is the GPA versus time spent studying per day. So, what is mathematical models? The formal definition is a description of a system using mathematical concepts and language. By a system, it means just any kind of group that we make. It's like it's a group where the entities inside there interact with one another. It's going to be, the concept of a system is going to be more clear as I go into the system dynamics model, which is at the end of this presentation. But for now, I'll just bear with this definition. So let's take an example of how that definition is applicable in each of these situations. In here, we use the mathematical concept of log, like ln, which is a logarithm, the concept of logarithms, in order to describe the system of students spending time studying each day and then getting a GPA. On the other hand, in here, the system in this model is in vitro, which is basically tissue growth inside a test tube. So the tissues inside the test tube is the system as being the entity in this scenario right here. And we use the set of differential equations in multivariate calculus, which is also a mathematical concept that was used to describe what is actually happening inside this system here. Or is this clear? How do we actually construct these models? So there are mainly 7 steps when you're trying to make mathematical models. Because this is basically mapping something happening in the real world to the math world. So that is, after you identify a real world problem, you describe it and then specify the mathematical problem that's actually inside there. So in the previous one that Joshua and I did, which was Hyamsey and Basel's battles, the topic was basically about after a certain regulation is introduced into a certain region, how much would the plastic bottle sales decrease? So here, that's the real world problem here is just basically environmental pollution, and the mathematical problem is formulating that into equations and formulas to basically describe how much the bottle sales are going to decrease. So that's the process where you go from this stage to this stage, where you formulate the model and make actual equations, and then you solve the mathematics from that. After solving the mathematics, you get the results, which you can interpret the solution just as you would do for a science report. When you're doing a science report, you would get data from experiments, and then you would analyze the data, tell the reader what this number means, what the x-intercept means, what the gradient means, and so on and so forth. That's how you interpret the solution and indicate what each of the numbers in the mathematical model and the results actually tells to our society. Then the final thing to do would be evaluating the model, which is just as in a science report, talk about the limitations, the conclusions, and evaluate the credibility of your model. But in some cases, it's just impossible to make a 100% accurate model. So take the example of maybe like predicting the weather. We use Navier-Stokes equations, but because we do not have because we did not find the solution for that equation, we use like recursion systems. We just we repeat the calculations so much that it becomes really, really close to reality. But the problem is, there's still that kind of difference. And that difference between reality and your model is what you talk about in this section here. But in some cases, the difference might be quite big. The inaccuracy might be very large. Then you go back to the stage, you specify the mathematical problem again, but with greater accuracy, and you improve your equations by taking other factors into consideration. So this is the endless loop where you repeat this until you get a fairly accurate result. Then, after you get the results and you think that your model is credible enough, you will go to the reporting stage where you write a formal math paper for that. But the thing is, even though we know how to make all models, this complicated system of equations here and this really easy logarithm equation looks quite different. And that's because the way in which these two things are made is very different. So, if you look at this example here, which is discrete models for in vitro tissue growth, we haven't done this yet. You do not have experimental, the person who made this model did not have experimental data when he was making this. On the other hand, here we have a set of data points. We have actually a lot of data points that we can extrapolate this equation here from. And hence, we have two different ways of constructing models inside the 7 stages. The first one is a Whitebox method, where you have ample a priori information. A priori information is basically a fancy word for the types of data that you have before you're actually constructing the model. And here, the Whitebox method is when you have all the necessary information that's needed. But on the other hand, the Blackbox method is when you have no a priori information. And hence you need to decide the variables about what kind of things you're going to take into consideration, and then you make all of those into this set of equations by considering the physical relationships between each of the variables, by thinking about the interactions between each of the variables that you're going to take into consideration. But in most of the cases, most are a combination of white and black box methods. Because if you think about the example here, which is spread of a certain medicine in the human body, we could have experimental data, but we still do not know everything about this medicine, about how this medicine actually interacts within our body. Maybe we might not know how much time it takes for this medicine to be released from our bodies. So most of the times, human beings do not have knowledge about every single thing inside the system. So that's why we use a combination of white box and black box methods. And also a very important implication from this is that in black box methods, we decide the variables, what kind of things we're going to take into consideration, which means that it is not necessarily identical to reality. It can have like a kind of difference. And hence, all models are wrong. This is a very important and famous aphorism that's used in data science, that all models are wrong because they are basically a mixture of white box methods and black box methods, and black box methods at the end inevitably produce at least some inaccuracy. But some are close enough to reality that they are good to use, and these are the types of models that we are trying to find. And then, how do we make those models more reliable then? The aphorism under that is that multiple heads are better than one. In non-numerical models, where you just qualitatively compare two things, we have the condensate jury theorem to prove this claim, and in the case of numerical models, we have the diversity prediction theorem to prove this claim. So firstly, about these non-numerical models, where you just compare the two and say that probably this one is going to be larger than the other one. We use the condensate jury theorem. So that is, let's say that there is n number of people, and the number of people inside a system is odd. So we have a 3, 5, 7, an odd number of people. And each person has a binary choice. So you vote for either true or false. And each person has an accuracy of 1/2. These are the 3 preconditions for this theorem. Then if these 3 preconditions hold true, the more people we have, the more the accuracy of the vote actually approaches 100%. So if we change this to the context of models, because the models make a qualitative judgment, you only have true or false. A is bigger than B, or B is bigger than A. So there's only binary choices. And also, let's say that we have an odd number of models. And because in the previous stage, I told you that models have to be at least reasonably accurate. So let's say that each model has an accuracy of 1/2. Then the more models we have, the majority vote is going to approach, the accuracy of the majority vote is going to approach 100%. And to prove this, you can just use the binomial expansion, and that will give you a pretty straightforward proof. And on the other hand, for numerical models, you have the diversity prediction theorem to prove that many models are better than one. To prove this, you can just basically expand each of these sides, and then it's going to also give you a very straightforward result. But what this in essence tells you is that this is the crowd's square error. C is the average of crowd prediction, and X is the actual value. So if you sum all of these up, you would get the sum of the square error, right? But in this case here, this gives you the mean square error because you're now dividing this whole thing by n. And then here, this is the equation for the diversity of the crowd. So this means that the crowd's square error equals mean square error minus diversity of the crowd. Which means that the more diverse the crowd becomes, the smaller the crowd's square error will become. And the implication and the reason behind this is you could prove this by just literally expanding each of the terms, but you could also say that the positive errors just simply cancel out the negative errors when you have many models, and hence the result will approach reality when you have many models. So finally, a bit more fun mathsy stuff. Applications into system dynamics models. So system dynamics models are basically models in which the relationships between the entities depend on one another. So let's take the example of a moose population and a grass population. If you have more grass, the moose population would increase. Well, if the moose population increases, they would eat more grass, and the grass population would then decrease. So there's this continuous cycle that affects the variables and entities of each other, and those are basically called system dynamics models. So please take some time to read this excerpt here. So we go back to this stage. First, we describe the real world problem and then map that into the real world, the math world, sorry. And then we do that by constructing this diagram here. M equals moose population and W equals the wolf population. Plus is when this positively affects this, and minus is when the wolf population negatively impacts the moose population. Here you have this plus because the more moose you have, the more food that the wolf has. And the more wolf there is, the less the moose number is going to become because wolf prey on moose. The reason why there's this circle here is because they reproduce and produce new offsprings. Then there's also a minus to consider in both entities because moose also die off as well. Then we specify the mathematical problem. We're going to establish continuous models, which means that we're going to make differential equations about the rate of change of each of the populations here. Then by specifying the mathematical problem, we will consider the situation to be identical to random collisions between moose molecules and wolf molecules, just as we would consider in a gaseous system. Then we set the variables like this: M equals moose population, and G equals moose population increase without wolf, and so on and so forth. Essentially, what we're trying to do is to establish an equation for each of the interactions, each of the arrows here, and then sum that up to describe the moose population, and the other equation is going to be about the wolf population. So here we use Newton's notations. So the rate of change of the moose population would equal growth rate minus rate of predation. And in rate of predation, we will also include just this death rate as well. So it's basically birth rate minus death rate. For the wolf, the same will apply. The rate of predation, because the more moose the wolf eats, the more offspring that you will have, because there becomes more wolf. And then we will subtract the decline rate from that, which would be this thing here, the death rate, and this arrow here as well. So it's actually kind of like physics, where you identify the pluses and minuses for each of the variables, and then sum that up to make equations. Then first, we change the growth rate would become GM, when G is the moose population increase rate. If you multiply increase rate by the population, that would be the rate of increase. And here, the decline rate will be moose population decline rate when moose and wolf meet, which is A times N times W. Because this is basically the probability, because N times W would be the probability in which the two meet, and then if you multiply A, that would be the probability in which a moose dies off. Using the same method, we also represent this dw dt as this equation right here. Then, because we have now mapped the real world situation successfully into the math world, we now solve the mathematics and see what each of the numbers, what each of the solutions actually mean to us. So firstly, we see an equilibrium. So the interior equilibrium inside the system is when F equals G over A and H equals D over B. And what's really remarkable, and what we can actually see from this thing here, is that what happens to each of the populations does not depend on the wolf birth rate and the moose death rate, because both of them are not inside this equation right here. And then we can also infer that extinction would happen when both of these are 0, so when G and D are 0, the extinction would happen, and so on and so forth. These are the kinds of inferences that we can make from these solutions right here. And using some advanced softwares like MATLAB or Mathematica, we can also construct a graph of what would actually happen there. By inputting the initial values, the initial data that we have, we get the result of this kind of cycle here, where the prey continuously increases, and then the predator also increases, but then they plummet at around the similar time. Then after we get the entire mathematical solution, we would evaluate the model. We would bring data from other islands where there's a large population of moose and wolf. In this case, I use the example of Isle Royale, a place called Isle Royale where you have a large moose population and a wolf population. Here, this is the graph that represents the population of the wolf population and the moose population. And by looking at this graph, you can basically compare this with the mathematical solution that you obtained and evaluate how credible and reliable yours is. And also in the evaluation, we will also want to talk about what the model actually means. The formal name for these set of equations is called a Lotka-Volterra equation. And we can also talk about implications, such as how this can be basically implemented in disease modeling, such as SIR models, where the susceptible population, infected population, recurrent population interact with one another. We could also use this for any predator-prey situations, and we can also use this for any number of predator and prey actually. So, are there any questions? Yay! Thank you.